Okay, so we're continuing with measuring rates of reaction, and we're going to look at the effect that different factors that influence reaction rate have on the reaction rate. Now, this textbook has a lot of information and I don't want you to stress over it. You can just read over it, but whatever I'm explaining to you now, that is what I want you to focus on. Now, it's going to be long, so you might want to get some popcorn or coffee or something, but pay attention at the same time. Right, so let's first look at concentration. So the effect of concentration on reaction rate. Now, if you look at this, they basically done a whole lot of experiments here, and they try to show you how the different factors affected reaction rate and how they are related to reaction rate. So the first thing they did was do an experiment looking at concentration. Now, if you looked at the experiment they did, it was with sodium thiosulfate plus HCl, giving you sodium chloride plus water plus sulfur dioxide plus sulfur, which is a solid. It's a yellow sulfur precipitate, which is a yellow solid. Now, what they did here is, since it's a solid, they did that style where you have an X in underneath on a glass beaker, and as the reaction is happening, you are forming product, and that product solid is going to cover that X mark. So from that you can measure how much solid is being formed and see the reaction rate. Now, if you look here, this reaction was all about changing the concentration of the reactant, and it was particular this sodium thiosulfate solution. Now, if you look here, you have different flasks A, B, C, D, E, and each of these flasks have a different amount of sodium thiosulfate and a different amount of water. Now, water is how you change concentration. The more water you add to something, the less the concentration will be, and the less water you add, the more concentrated it will be. It's like OROS. If you add more water, it will be more dilute. If you add less water, it will be more concentrated. Now, in different flasks, they added different amounts of sodium thiosulfate, and as you're going from A to E, you decreased the volume of sodium thiosulfate, and centimeter cubed is the same as milliliter, and it deals with volume. And as you're going from A to E, at the same time as decreasing sodium thiosulfate, you increased water, which means the more water you're adding, the more dilute you're making it, so the concentration is less. So as you're going from A all the way down to E, concentration is decreasing, and the total volume of both the water and the sodium thiosulfate together must give you the same amount, but only now the concentration will be different. So this is how they change concentration, by adding different amounts of water to different amounts of the sodium thiosulfate reactant. And then they did the reaction, and then they got these results showing how the concentration of reactant affected the rate of reaction. Right, now here's the volume of that sodium thiosulfate that they used. This is the volume of water added, and this is the concentration that they had. Now, this is what we're going to be focusing on, the concentration. Now, as you're going down, can you see that the concentration is decreasing? And we know from theory that if concentration decreases, then automatically rate of reaction will decrease, and we'll see that now. Right, so then they measure the time it took for the cross to disappear, which is basically the time it took for the solid to form. And as you're going down the table, you can see that the time is increasing. Now, remember I told you, time and rate is not the same thing. They are inversely proportional. So we don't really care too much about time. We care more on the rate of reaction, which is 1 over time, which is either concentration over time, moles over time, mass over time, or whatever kind of quantity you're using. Right, so the time is more, but since the time is increasing, we know that rate of reaction should be doing the opposite, so it should be decreasing. And if you look here, you can see that rate of reaction as you're going down the table is decreasing from 0.023 all the way down to 0.0041. So if you're looking at the concentration and the rate of reaction column, you can see that as concentration is decreasing, rate of reaction is also decreasing, which is what we expected. Now, all of this experiments is just to show you examples in real life how the different factors do affect rate of reaction. Now, if we take all of this information and plot it on a graph, you will get graphs that look like this. So this first graph is the graph of time versus concentration. Now, we said time and rate is not the same thing, so we won't really expect too much information from a time versus concentration graph. But from this graph, you can see that as time is going on, the concentration is actually becoming less, because rate of reaction is inversely proportional to time. So you won't expect time to be increasing with increasing concentration. It will actually be decreasing, or the other way around. But if you look at the rate of reaction graph, can you see that this graph is a straight line, and if you extrapolate it, it will actually go through the origin. And anytime you have a graph, a straight line graph that goes through the origin, automatically it tells you that you have a directly proportional relationship between rate of reaction and, in this case, concentration. So when you're plotting a rate of reaction versus time versus concentration graph, can you see that you have a straight line graph? And this tells you that rate of reaction is directly proportional to concentration. Now look at the difference between the time concentration graph versus the rate of reaction versus the concentration graph. Completely different. This one is a curve and it's showing an opposite relationship. This one is a straight line graph and showing a direct relationship. So this just emphasizes how time is the opposite of rate of reaction. And when you're looking for rate of reaction, we don't really care about time. We care about 1 over time, which is the rate of reaction. Okay, so from here we can see that rate is directly proportional to the concentration of the sodium thiosulfate solution, which is the reactant. So that is an actual real evidence from a real life investigation how concentration and rate of reaction are directly proportional. So if you double concentration, the rate of reaction will also double. If you half it, the rate of reaction will also become half, or it will become slower by 2. Right, let's look at another example also focusing on concentration. Now here you have this reaction, which is magnesium plus hydrochloric acid giving you magnesium chloride and hydrogen gas. Right, now this reaction we are dealing with a gas, in specifically hydrogen, and we're dealing with HCl solution, and we are going to see different effects of the HCl solution with different concentrations. So the first graph, we're dealing with a concentration of 1 mole per decimeter cubed. The second graph 0.8 and the third 0.6. So as you can see, as you're going from 1 to 3, the concentration is decreasing. Now, they drew graphs that correspond to each of these experiments. And can you see that graph 1, which has the highest concentration, is actually the most steepest. It's more with a higher, it has basically a higher gradient, which means that this reaction is happening faster. The higher gradient you have, the faster the reaction is happening, because gradient is actually equal to the rate of the reaction. So graph 1 has a huge gradient because it's more steep, which means a higher concentration will result in a higher gradient and a higher rate of reaction. And as you go into graph 2 and 3, it's still increasing. It's still an increasing graph, but it's not increasing as rapidly as graph 1 because the concentration is less. So from these experiments, you can see firsthand that concentration has a directly proportional relationship to rate of reaction. Okay, let's look at the next factor, which is temperature and how temperature affects reaction rate. Now we're looking at the same reaction, which is involving sodium thiosulfate again with hydrochloric acid. Now this one is quite straightforward. As you can see, you just have different experiments, and in each experiment you are changing the temperature. So you're going from 20, increasing it all the way up to 60, and here can you see that the concentration of the reactant is staying constant, because we are trying to find out the effect of temperature on reactant rate, which means everything else must be the control variable. It must not change, so we have to keep concentration the same. So if ever you see something is staying the same, it's because there is the control and we are trying to find out the effect of something else, and in this case it's temperature. Right, so as temperature is increasing down the table, can you see that the time is actually decreasing? But if you look at the rate of reaction, it's increasing from 0.0036 all the way to 0.059. So again, can you see time and rate of reaction? They are opposites. So if you're looking at temperature and rate of reaction, as temperature is increasing going down the table, rate of reaction is also increasing. And this is exactly what we expect, because as you're increasing temperature, you're increasing kinetic energy, which means more particles can collide effectively, resulting in a higher rate of reaction. And if we take this information again and plot graphs from it, we will get graphs that look like this. So again, here we have a time versus temperature graph. We're not going to worry too much about time because our focus is mostly on the rate, which is 1 over time. And if you look at this graph, you can see as the rate of reaction or as the temperature is increasing, the rate of reaction is also increasing. So they are both dependent. Their temperature affects rate of reaction very much. But if you compare this graph to the concentration graph, you can see that it is not a straight line going through the origin. It's a curved line. And that specifically tells you that temperature is not directly proportional to rate of reaction. They may affect each other. Temperature affects rate of reaction, but it is not directly proportional. What that means is temperature, if it increases, the rate of reaction is also going to increase, definitely, without a doubt. But it does not mean that if temperature is doubled, rate of reaction will double, or if temperature is tripled, rate of reaction will triple. So it's not directly proportional, which means whatever happens to temperature is not going to directly happen to rate of reaction. It just means if temperature increases, rate of reaction will increase, and if temperature decreases, rate of reaction will decrease, but not directly proportional. Right, let's look at another example, which is the same one involving the hydrochloric acid and hydrogen gas. So again, here you have 3 experiments, and each one is done at different temperatures. One is 80 degrees Celsius, then you decreasing to 70 and to 60. And again, if you look at experiment 1's graph, it is the steepest from all, which means if it's more steeper, you have a higher gradient, and the gradient is equal to the rate. And so a higher temperature means that the rate of reaction is more. So this is just a second experiment that confirms this. Now, the important thing to know is temperature will affect rate of reaction. If it increases, rate of reaction will increase, but it is not directly proportional. It is just related, but it's not like concentration where you have a directly proportional relationship. Okay, so the third thing we're going to focus on is looking at the surface area and its effect on reaction rate. Now, when we're dealing with surface area, it only applies to solids. So we have to use a reaction that involves solids and a solid reactant, not a solid product. Now, in this case, we're dealing with calcium carbonate, and here it is a solid, which means we can take that solid and change its state, either make it more, have more surface area or less surface area, depending on how we break it up. Now, this reaction, it may seem a bit confusing, but just listen to what I'm saying. It will make sense afterwards. Right, so this is basically the results of this reaction. So you have investigation 1 where you're using large pieces of calcium carbonate. The large pieces means you have less surface area. So surface area for the large pieces will be less. And we already know from theory that if you decrease surface area, reaction rate decreases. Then you have investigation 2, which is the experiment where you're using calcium carbonate in powder form. Now in powder form, you're crushing it up small, which means the surface area is more, it's higher. And we already know if you increase surface area, reaction rate is going to increase. So we're going to expect an increase in reaction rate for investigation 2. Now let us look at the actual numbers here. Now if you look here, you can see this is the time that the reaction is happening for. This is the mass of flask and content, and this is the mass loss. Now this may not make any sense, but we're going to do a section after this called equilibrium, and then you'll see how it actually ties in with that. Now if you're looking at this mass loss column, you can see that at the end here you have 2 numbers which are identical. They are both 1.85. At 330 seconds and at 360 seconds you have the exact same mass loss, which means nothing really changed from this time. It's staying constant. Now when the numbers start to stay constant, we say equilibrium has been reached. Now don't worry too much about that, but just know that equilibrium means the reaction is now remaining constant. Nothing's going to happen after that. It's almost like the reaction is finished. It's not going to change anything now. So from 330 seconds, the reaction has reached equilibrium, which means that the reaction is now on a standstill. Nothing much is going to happen after this. Now if we look at investigation 2, can you see that we have reached equilibrium, which means we have the same constant numbers from 240 seconds all the way to 360. So from 240 seconds, we have reached the same number. Nothing has changed at all. Now, if you're looking at investigation 1 and 2, can you see that you have reached equilibrium at 330 seconds for the first investigation, and with the second one you reached it at 240 seconds. So you have reached equilibrium in both cases, but in investigation 2 you reached it at a much faster time, 240 seconds, which means the reaction happened faster because equilibrium was reached faster. So anytime you see something staying constant at a faster time or at an earlier time, it means that the reaction is happening faster. So this investigation just proves that because equilibrium is reached faster when you're using a powder form of the solid reactant, it means that the surface area does affect reaction rate, and the higher the surface area, the faster the reaction will be. And again, if you go to the next page, you can see here's another graph showing the different surface areas versus reaction rate. And if you look at graph 3 is when you're using an effervescent tablet in finely ground powder. So here you have a high surface area because it's a powder. In graph 2, it's broken into pieces, so it has a high surface area but not as much as a powder. And for graph 1, it's a whole effervescent tablet, so it's a big solid particle. It's not really broken down, so you have less surface area. And if you look at this graph, can you see graph 3, which corresponds to the powder with high surface area? That one is more steep, which means the gradient is greater, which means rate of reaction is greater. So the reaction is faster for a finely ground powder. And that is the same example with Grandpa. Grandpa, it is a powder kind of medicine for headaches, and because it's a powder and it has a higher surface area, it actually works faster. Oh, that's the theory. So from this reaction we see that the rate of the reaction increases as the solid substance surface area increases. So anytime something is broken down into a powder form, the reaction will always be faster.